Okay, so today we're going to talk about linked lists, locking, lock-free, and beyond. It's chapter 9 of the book. And in the last lecture, you may recall, we talked about spin locks. And what we did is when we got a lock, we entered the critical section, and then we reset the lock when we exited. Today, we're going to talk about concurrent objects. Adding threads should not lower throughput, obviously, otherwise why do it? But we have to deal with contention effects, and many of those were fixed by the Q locks. The original contention effects that we saw from, say, the TAS lock was fixed by our Q locks. Today, we're going to work on how to see if we can increase throughput. So this isn't possible if our application is inherently sequential, like if we're just adding integer. Well, even if we're just adding one repeatedly to an integer, it's possible to parallelize that, because what you could do is you could take it into batches and have each thread increment the batches, and then. But anyway, there are some computations that are inherently sequential, but surprising things are parallelizable. So the first thing we're going to discuss is coarse-grained synchronization, where each method locks the object and contention is avoided using a Q lock. And the nice thing about this is it's easy to reason about in most cases. So are we done? The answer is going to be no, of course. The problem with coarse-grained synchronization is that we have a sequential bottleneck. The threads stand in line, and adding more threads doesn't improve throughput. In fact, we have to struggle to keep it from getting worse. So, if this is the case, why even use a multiprocessor, right? If you have this much trouble getting things to actually be parallel, and of course, there are some applications and some problems that are inherently parallel, and those can benefit. So what we're going to do today is we're going to introduce 4 patterns for parallel programming. And this is a bag of tricks. It's a set of methods that worked more than once. And for highly concurrent objects, it will give you more concurrent access, and more threads will give you more throughput. So the first improvement we're going to try to make is fine-grained synchronization. So instead of using a single lock, we're going to split the object into independently synchronized components. And then the methods will conflict when they access the same component at the same time. But otherwise, if they're not accessing the same component at the same time, then they won't conflict. The second optimization we're going to talk about is optimistic synchronization. And then we're going to search without locking. And if you find it, lock it in check. And then if that's okay, then we're done. Otherwise, we start over. And this is usually cheaper than locking, but mistakes are expensive. Next, we're going to discuss lazy synchronization, in which we postpone the hard work, but removing components is tricky. So we're going to have a logical removal where we mark things to be deleted, and then a physical removal where we actually do the removing. And fourth, we're going to have a lock-free synchronization where we don't use locks at all. We're going to use relatives of compare and set. And the advantages here are that we have no scheduler assumptions. The disadvantages is it's more complex, and sometimes there's a high overhead from doing all this additional logic. I don't expect these four items to make complete sense right now, but after we go through the lecture, hopefully they will. And if you're reviewing, if you're watching the lecture again to review, that this will sort of help you frame your thoughts. So we're going to work with a linked list, and we're going to illustrate these patterns using a list-based set. So this is a fairly common sort of application, and it's a building block for other kinds of applications. And the set interface means that we have an unordered collection of items. We have no duplicates in the items, and we have methods add, remove, and contains. Okay, so this is the basic concept of a set. So if we're going to, and we're going to implement this with a list, so that we have the add item to the set, a remove item from the set, and a check to see if the item is present in the set. And all three of these things have Boolean return values because they can all succeed or fail. Add will fail if the item is already there. Remove will fail if the item is absent. So we're going to have our linked list is going to be based on this list class called node, where it has an item, it has a hash key, and it has a pointer to the next node. So I know we said that a set is unordered, but for the purpose of this implementation, we're going to order items. And so the way our list is going to look is we're going to have two sentinel nodes, which are nodes that just mark the head and the tail of the set. And then in between, we're going to have the different nodes are going to point to each other. So this is a set that contains A, B, and C. So one of the things we're going to introduce now is the concept of an invariant, which is a vocabulary word which I can test you on. So an invariant is a property that always holds. And it's true when the object is created. And the truth of that statement is preserved by each method and each step of each method. So invariants preserved by add, removed, and contains. The invariants we're going to discuss are conserved by these methods. Invariants only make sense if the methods considered are the only modifiers. If there's some way to access the data and change it outside the methods, then you can't really use the concept of an invariant in any reasonable way. But language encapsulation helps, so you can say things are private and you can prevent other classes from getting in there and changing the data. So we need freedom from interference for removed nodes. So some algorithms traverse removed nodes, and we need to make sure everything works correctly. Now, for those of you who are fans of C or C++, this is going to be, these algorithms are going to be much more tricky if you want to implement them in that language, because in that language you have to pay attention to garbage collection. I mean, I guess you could just not do it, but getting the malloc and free to work correctly with all these things presents additional challenges, which trying to make malloc and free work in C++ with these concurrent algorithms presents additional challenges which we're just not going to discuss. So our abstract data types, we have a concrete representation. We have a concrete representation of our abstract set data type, which is this linked list with two sentinel nodes, and in this case, it contains A and B. And the abstract way of writing that would be just put A and B in curly braces like that. So the meaning of a representation given by this abstraction is like this. So this is our internal representation of how we're making the set work, and this is how we would write a set of just A and B. And so our invariants are going to be that we have sentinel nodes, and the tail is always reachable from the head, and that the list is sorted, and that it contains no duplicate. We have three invariants in this particular example. And we can always say that X, that if we say that it contains X, then there exists A such that A is reachable from the head and A dot item is X. So if this is saying that S contains X. So here's what an add looks like, and here's what a remove looks like. So we're going to start with A, and we're going to add B, and then we're going to have the list A, B, C, D, and then we're going to remove, and that's going to take the A. Or if we start with A, hold on, let me back up. If we start with A, C, D, and A, B, C like that, then if we want to add an item, what we're going to do is swing this pointer down to the new item and have the new item's pointer go to here. When we remove an item, we want to swing this pointer from here to here. Now, we haven't drawn the tail sentinel nodes in here, but in this case, they're obviously going to be unaffected. Now, let's suppose we're writing code for the add method. Now, one of the things we said was that we're maintaining an invariant that says that the tail is always reachable from the head. Okay, what that means is that prior to setting this pointer from A to point to the new node, we must already have set this pointer from B to point to this node C. Because if we did it in the other order, right, we'd break that invariant. Do you all see that? Does anyone not see that? Is anyone alive?
Yes.
Yeah, that makes sense.
Yes.
Yes.
Okay, great. Just check for life science. Okay, so coarse-grained locking, which was the first thing we wanted to discuss, we're going to get a lock on the head node, and then we're just going to do our thing. So in this case, we're adding a node C. The problem, of course, is everybody who wants to use the list has to line up, and there's a congestion, which, you know, if threads had horns, they would be honking. It's simple, but we have a hotspot right here, and we have a bottleneck when many threads are trying to access that object. So coarse-grained locking is easy. We have one lock to rule them all, and it's simple, and it's clearly correct. And that's a thing that deserves respect. You know, very often, if you're implementing some more complex code, you want to put something that's simple, clearly correct, and inefficient in to start with, just so you have some ground truth and you know what you're doing. Unfortunately, this simple, clearly correct method works poorly with contented. Q-locks can help, but the bottleneck is still there. Fine-grained locking requires careful thought, and we have a quote from the Lord of the Rings to illustrate that. Do not meddle in the affairs of wizards, for they are subtle and quick to anger. The idea is we're going to split the object into pieces, and each piece will have its own lock, and methods that work on disjoint pieces need not exclude each other. Now, fine-grained locking always requires careful thought. Can anyone tell me a reason why that might be true?
You need to make sure the two parts don't depend on each other so they don't collide in any way.
Yeah, I mean, sure, that's true. I'm looking for, though, we have a term that a word that you were tested on, and it's a thing we said about programming with locks. Does that ring a bell with anyone? So if I just show you a piece of, if I have a big application, you know, hundreds of thousands of lines of code, and I show you some routine in the middle of that routine, of that huge code base, and I ask you, yes, composability, exactly what I'm looking for. Locks are not composable. You have to sort of understand everything that's going on in the application before you can really program in locks. You can't just look at the pieces in isolation. So fine-grained locking is always going to require careful thought because of that. Okay. So in this case, what we're going to do is hand-over-hand locking. And the point is we're gonna lock two objects at a time. And when we want to lock the third one, we'll give up this lock and we'll grab this lock. And likewise, we'll just get these two. So we're always going to have a pair of nodes locked. But we're not going to lock the whole thing. So while we're doing this, someone else could, in principle, lock the front. So removing a node is going to look like this. We want to remove B. We wait till we get A and B locked, and then we're going to swing A's pointer over to point to C. And now B is removed. So the question you might be asking yourself is, why hold two locks? Why not just one? Well, it's going to go like this. Suppose I want to remove C. Okay, and I've got B locked, and what I want to do is swing this pointer over here, right? And now what I've got is I want to remove B also. So these are each holding the locks with the pointer that they want to change. And they're both ready to remove their objects. Now, this orange processor is going to go first. It's going to swing the pointer from the next pointer on B to point to D, and that will remove C from the list. And now, before it even gives up the lock, A is going to remove B by swinging its pointer, and it's going to swing it to C. And this is a thing that can happen, right? And so what goes on here is C didn't really get removed. The orange processor's work was undone. So to make sure that this kind of thing doesn't happen, we're going to always hold two nodes. Okay. So to delete node C, we swing B's next field to D. That's clear. But there's a problem if someone is concurrently deleting B. They could redirect the pointer to C. So if we have two locks, so if we lock a node and its predecessor, then it works. Does that make sense? Does it not make sense? Are there any questions?
Can you explain again why you're removing two instead of one? Like, I understand it's to do the dual removing, but I guess I'm just a little confused still.
Okay, so here's the thing. What happens is, all right, I get to this stage. Now what's going to happen is A is going to say, what's B's next pointer? It's going to say, actually, let me back up one more. Okay, so the two codes are, the code is like this currently. And now on the green processor, what we're going to do is we're going to say, what's B's next pointer? B's next pointer is C, right?
Right.
So we're going to remember that because to remove B, we're going to update our next pointer to point there. But now the orange processor comes in and it's removing C, and it's already got the lock on B. So it looks at C's next pointer and says, oh, that's D. So now I'm going to update here and I'm going to swing this to here. Okay, so now B has removed C by updating its next pointer. But now A was partway done. It had read B's next pointer and knew it was pointing to C. And so it knows that to delete B, it should update its next pointer to point to C. The problem is the list now starts from the head to A to C to D. Okay. And this operation that the orange processor attempted to do, the removal of C, failed. Nothing happened at all. Do you see that?
Yeah, because A kind of brought it back in by making its next C.
Right. So if we had locked both of these nodes, if the green processor had locked both of these nodes and it looked at B's next pointer, it could be sure that next pointer wouldn't update while it was setting its own next pointer. And this can be removed. This can be avoided. Got it?
Yeah.
Thank you, Brandon, for asking and not sitting quietly and allowing your confusion to remain. So, all right. So the next thing we're going to look at is we're going to look at hand over hand again. We're going to remove B. Okay, and we found it. And so we're going to swing our pointer and remove it. That part should be familiar and make sense. Okay, now we also have remove C in the picture. Remove C is going to come through. Okay, and now they're both working at doing this. but the orange processor is ready to remove C. It's got both locks. It swings the pointer from B to D, and C is removed. And now the green processor can continue. And when it locks B, it's going to see the correct thing. And now both B and C are successfully removed. So that's how that looks when we hold both locks. Everybody okay?
Yeah, I'm sorry, can you just show that transition one more time?
Yep, absolutely. Just okay, here we go. All right, so we start. C begins first. C has got A. C has got AB. The green has got the head node. Green has got the first two nodes. Orange has got the second two nodes. Now, green can't advance, right? Because it must acquire the lock for B, and the lock for B is held by the orange one. So it stops. It's blocked. Now, the orange one is trying to remove C, and it's holding those two locks. So it's able to look at the value of C's next pointer and then copy that value into B's next pointer, and that will remove C. And now it's done. And now, because it's freed up the locks, the green processor can get the lock to B. And now, because it's got the lock to A and B, it can look at B's next field and copy that value into A's next field in order to remove B. And that way, we both succeed. Two concurrent removes succeed. Make sense? Happy?
Yes, thank you.
Okay. So here is a remove method. We get a hash code for the item. And we're going to assume in these slides that the hash code uniquely identifies the item. I mean, this isn't necessarily true of hash codes in general, but this is a highly simplified case. And it's just easier if you think about it that way. Okay, so next we're going to look at predecessor and current nodes. These are two concepts we're going to have. So if we want to delete the current node, we need to hold the predecessor's lock. And then, of course, we're going to do this try finally thing to make sure that we always unlock things the way we're supposed to. And everything else is going to go where that ... is. And that's going to look something like this. So we're going to get the predecessor from the head. We're going to lock the predecessor. And then we're going to get the current from the predecessors next. And then we're going to lock the current. So we're always locking things in the order we're always locking nodes in order from the beginning to the end. So this is locking the predecessor. This is getting the next one and locking that. And then we're going to traverse the list. And to traverse the list, first we're going to search for the key. And we're going to find out if the item is equal to the current item. This will only work in Java, of course, if you've got a primitive type as your item. And it won't even work for a wrapper to a primitive type, but that's a Java detail we don't need to really discuss too much. So if the item is equal to the current item, then we're going to say pred.next is cur.next. Okay, this is how you remove. So this is, you saw that arrow swing from, like A to C. This is how it's done. We take the next pointer here on the predecessor and we make it the same as the next pointer on the current item. And then we can return true. Does that make sense?
Yeah.
Okay, and then we can do the if this doesn't happen, now we have to step the locks along. So what we're going to do is we're going to unlock the predecessor lock. We're going to update the predecessor to be the current. We're going to update the current to be the current.next, and then we're going to lock the current. So now we're back to holding two locks. and our lock invariant is restored. And otherwise, if this fails, then we tried to remove something that wasn't in the list. So adding nodes, we must also lock the predecessor and the successor, and neither can be deleted. There's a little question for you. Is the successor lock actually required? Okay, so it's easy to check that the tail is always reachable from the heads, and the nodes are sorted with no duplicates. That's our invariant with this fine grained lock. And the drawbacks are, well, okay, so it's better than the coarse grained lock. Threads can traverse in parallel, and it's still not ideal. For long changes of acquires and releases, it's inefficient. And so the next thing to look at is optimistic synchronization. We're going to find nodes without locking. Then we're going to lock the nodes. Then we're going to check that everything is okay. So we searched from the head and we found the pair we wanted. We want to add C in the middle of between B and D. And so we're going to lock those. Then we're going to insert C. So what could go wrong with this? So let's look at it happening again. We found out the pair that we want to work on. All right. But now someone else comes in. This orange processor comes in, locks A and B and removes B. Now it's done. And A is pointing to D, and we lock B and D, not realizing that B is deleted. And then we insert C between B and D. But this obviously has no effect, right? Because B is no longer reachable from the head, and therefore C is no longer reachable from the head. So add C did not take effect. So we're going to try again. And what we're going to do is after we lock it, we're going to check that we can still get from the head to B. Let me just back up and show you that again. So the validate step is what we're going to do next. So we discovered what could go wrong with just locking these two nodes after we found them. So what we have to do is after we find them and after we lock them, then we go back and we validate that we can still get there. So we know that B is still a valid node that way, and we can safely insert C. The other thing that could happen is after we find our two nodes, but before we insert them, someone else comes and adds B prime in between B and D. Okay, now we get our locks and we verify that we can still reach B from the head and insert C, but what we've done is we've undone this insertion of B prime, and we don't want to do that either. So the other part of validation while holding the locks is we're going to check that B still points to D. So we've checked two things. First, we can reach B from the head, and second, that B still points to D. And only if those two things are true are we safe. Any questions? Does anyone need to see that again? Okay. So we want to have a linearization point for everything that we do, some point at which C is present, and then we can safely add it. So we have to be careful when we preserve our invariants when we do things, and that we have to be aware that we may traverse deleted nodes, but we establish properties by validation, 2 steps of validation, and we do that after we lock our target. So correctness, if nodes B and C both locked, node B still accessible, node C still successor to B, then neither will be deleted. It's okay to delete and return true. So here is an unsuccessful removal. We've got B and D. Aha. We lock them. We verify, validate, yes. B still reachable from the head. And then we go to remove C. So that's gonna fail because there is no C. And so correctness, as I said, if B and D are both locked, B is still accessible, D is still the successor as before, right? It's okay. No thread can add C after B while we've got all of that. So let's look at some code. We're going to have a validate routine that's going to take a predecessor and a current node. We're going to initialize our node variable node with the head. Okay, and then we're going to loop through this while the node key is less than the predecessor key. If the node is equal to the predecessor, and if the predecessor's next is equal to the current, all right, that means we found a pair of nodes where we found the predecessor and the current nodes, and we're going to say that and if this is true, it's going to return. Otherwise, we're going to move on to the next node. And if we don't find it, we're going to return false. The predecessor is not reachable. So when we go to remove a node, we're going to get the hash code. We're going to go into an infinite loop, but we're going to retry. We're going to have this retry label so that we can start again on a synchronization conflict. We're going to get the predecessor and the head from the head, and the current from the predecessor next. Excuse me. We're going to loop through the nodes. Well, the current key is less than or equal to the key. If we find the item that we're looking for, we're going to break. And otherwise, we're going to move along. So this is going to find things, and then next we would validate and so on. So the item is, so on exit from this loop, if the item is present, the current holds the item. Predecessor is just before current. If the item is absent, the current has the first higher key and the predecessor is just before current. So here is our remove method. We have a try and an unlock. We lock both. We validate that the predecessor and the current are, what they're supposed to be. And if the current item is equal to the item, then we're going to do the removal. This is the removal step, and then return true. Otherwise, we'll return false. That was, this whole slide here is the ... on the previous code slide, of course. Okay, and we return false here. That means the target isn't found. We were trying to move C from a list that didn't contain C, for example. Okay, so the optimistic lock has limited hotspots, right? The add and the remove and the contains method can happen. We have no contention on the traversals of the list, so that cuts down on our locking. Moreover, the traversals are weight free, which should be food for thought, because weight free and lock free are things that we like to have. So far so good. We have much less lock acquisition and release, which is good for performance and concurrency. The problem is we need to traverse the list twice, and the contains method acquires locks. Optimistic is effective if the cost of scanning twice without locks is less than the cost of scanning once with locks, which it may or may not be. And the drawback is that contains acquires locks. And we're going to assume that in our applications that we're building for, that 90% of the calls are to contains. So next we're going to discuss lazy list. Are there any questions on optimistic list before I proceed? Okay, I don't hear anything. So lazy list. So this is going to be like optimistic, except that we scan once. Our contains method is never going to get a lock. And the key insight is that removing nodes causes trouble. And so we're going to do it lazily. So remove scans the list as before. It locks the predecessor and the current as before, but then it does a logical delete. It marks the current node as removed. This is new. And then the physical delete afterward. So it redirects the predecessor's next as before. So a lazy removal looks like this. We found the node we want to remove. We set this little flag from green to red, this logically deleted flag. And now anybody that sees this node can look at the flag and can tell that it's supposed to be deleted. And then we physically delete it by swinging the next pointer on B to point to D. Okay, and then we're physically deleted. Okay, so in the lazy list, all methods scan through the locked and marked nodes, and removing a node doesn't slow down the other methods. We still have to lock the predecessor and current nodes as before, but we don't need to rescan the list anymore. We check that the predecessor is not marked. We check that the current is not marked. We check that the predecessor points to occur. So the validation just requires these three simple checks. So how does this look? We have business as usual. Somebody comes in and decides to remove B. So I've got A and B. This green processor has got A and B, and then suddenly orange jumps in and removes B. It locks these two. Okay. It does its validation. It does its logical delete, right? And then its physical delete. Now green is going to resume its operation. And green is going to be able to tell if it's trying to do something like delete B. Also, it's going to see that B is already marked. It's going to realize when it goes to do a validation that this is marked, and the validation will fail for whatever it's trying to do, a remove or an add or contains or whatever. So validation looks like this. We check the predecessor is not logically removed. We check that the current is not logically removed, and that the predecessor is still pointing to the next one. Okay, so removal looks like this. If validation of predecessor and current, if the current key is the key, then we mark it as logically deleted. We physically remove it, and we're done. The contains method is going to get the current node from the head. It's going to cycle through while the current key is less than the key, and then it's going to, that's the way we advance through the loop. And then at the end, we're going to say if the current key is equal to the key and the current is not marked, then we're done. Now, so I guess this is why I said we assume that the key in the item, each key item has an exact key, has a one-to-one correspondence with its key, because otherwise this code would be wrong, right? This should be current item is equal to item. So the summary for wait-free contains is that we can use the mark bit and list ordering, and if it's not marked in the set or marked or missing, then it's not in the set. And so a lazy list can have add and remove plus a wait-free contains. So this is a huge improvement, right? Contains doesn't lock, it's wait-free. And this is good because we said that we were imagining we had 90% of our calls were to contains. And uncontended calls don't retraverse, which is nice. Bad is the contended add and remove calls do retraverse. You know, if they fail, right? and traffic jam can occur if one thread delays. So any concurrent data structure based on mutual exclusion has a weakness. If one thread enters a critical section and eats the big muffin, I don't know anybody but the people who write this book that use that term. But anyway, eats the big muffin, like this is a cache miss, a page fault, the thread is descheduled, whatever. Everyone else is stuck, right? Because it's a blocking algorithm. And so we need to trust the scheduler. On the other hand, lock-free data structures, no matter what, guarantee minimal progress in any execution. So some thread will always complete a method call, even if others halt at malicious times. And this implies that implementations can't use locks or shouldn't. So the final thing we're going to look at here are lock-free lists. It's the next logical step. Oh, and so before I go to lock-free lists, are there any questions about the logical deletion algorithm? The lock-free lists are going to use a compare and set to verify the pointer is correct. And so we're going to also use logical removal in this, just like we did in the previous one. All right. And then we're going to do physical removal. Okay. And using compare and swap, compare and set to verify the pointer is not enough. Okay. And we're going to try to show you why that happens. We try to do a logical removal. And then we do this compare and set to add a node. And then we go and do the physical removal. So what happened was this thing checked the flag, it saw green. It went to do the compare and set on this one, but in between this thing changed. And so the add failed. Does that make sense? Are there questions? All right, so the solution is we're going to combine a bit and a pointer into a single compare and set. Java has a special class for that. We have an atomic markable reference. And the mark bit and the pointer are going to be compared and set together. Okay, so what we're going to do is we have a logical removal set mark bit. And now when we do the cast, right, the part of the cast is going to be that this thing is still green. So it's going to say we have a next pointer and an unset logical removal bit that are going to get replaced with a pointer to this new object that also has its logical removal bit set to green. Okay, and so this will fail if anything marked this bit red. Okay, and so when this thing does its logical removal and then it does its physical removal, this step would fail. Any questions? So the atomic markable reference is the Java class. It will swing the reference and update the flag, and it will remove in 2 steps. So we're going to remove in 2 steps. First, we're going to set the mark bit in the next field, and then we're going to redirect the predecessor's pointer. The atomic markable reference class is going to take an address and plus a bit. So it's going to be a one big object. Actually, most of the times in address in the pointers that machines use, I think there are 1 or 2 bits that aren't used that you could just repurpose for this. But there are other ways of implementing it even without that. So the way this interface looks is we have on the atomic markable interfaces, we have this get method, and the get method is going to return the item, the reference to the item, plus it's going to return the mark bit. Now in Java, you don't things are passed by value, so you can't pass a Boolean in here and have it updated, but you can pass a Boolean array of length 1, and then the index 0 can be updated, and that's a way of passing a second value back. Does that make sense to people?
Yes.
Good. And then we have an is marked, which will return a Boolean. So you can just ask for that one thing. And our compare and set has 4 fields. We have the expected reference and the updated reference, and we have the expected mark and the updated mark. Okay, so if this is the current reference, if these two things match, then change both to these two things. So we can also attempt mark. If this is the current reference, then change the mark. All right, so removing a node now looks like this. We want to remove C. We set the logical flag to true. Now we're going to compare and set from B to D, and that will remove C. And we didn't have a lock. Now B, we're going to have B and C at the same time. So they both are going to mark. They're both going to do a compare and set, but only one of them will succeed, right? The A will succeed when it swings to C, right? This one will fail because it will discover that B has failed. B is removed. Okay, and so what's going to happen now is we can remove B, and then we're also going to remove C, because we're going to realize after we've done this that the flag has been set. And we're going to talk about how this other step happens. So the question is, when you're traversing a list, what do you do when you find a logically deleted node in your path? And the answer is you finish the job. You compare and set the predecessor's next field, and you proceed and you repeat as needed. So the observation here is it's not necessary always to do both steps. So long as you've marked the node as logically deleted, all is good. So we're going to have a lock-free traversal, only add and remove we're going to look at here. We have the predecessor and the current as before. We start to iterate through the list, and then we discover that B is logically removed. And so we're going to do a compare and set to swing the pointer from A to C. And so the way we're going to implement this is as follows. First, we're going to create a thing which we call a window class, which is going to have a predecessor and a current in it. And there's going to be a find method where we take a head and a key that we're looking for. And then we're going to, and that's going to sort of go through the list for us. And once we have a predecessor and a current, we're going to extract them from the window. And so first we do the window, and we find at some instant we have a predecessor and a current. Okay. And so we could have a predecessor and a current where this is some item that's in the list, and then we can redirect the pointer and take the item out of the list. So here is the remove code. You notice it's getting more and more complicated. So we have our while loop. We do a find. We get the predecessor and the current. If the current key is not equal to the key, then we return false. If the successor is equal to the current next reference, we get the successor, which is current item next get reference, and then we're going to try to snip out the current item, or we're going to try and mark the node as deleted. Rather, we're going to do a compare and set successor to successor, false to true. So that's just changing the bit from true to false. And if our attempt to do that did not succeed, then we're just going to continue. We're going to go back to the loop and try again. Otherwise, we're going to try and take the current node, take the predecessor's next field and set it to the current, from the current false to the successor true, and that will snip out the current node. Did you follow all that? Okay, so here is the add method. We're going to say, when we go to do the add, if the current key is equal to the key, we're going to return false because the item is already in the list. And then we're going to create a new node. Okay, and then we're going to set the next field equal to an atomic markable reference, and with current and false, this is going to point to the current node and the predecessor. And then what we're going to do is set the predecessor's next field to point to the current node with a false false. Okay, so this will install our new entry. And then we're going to have a wait for contains as before. So we're going to walk through the list, and when we find our success, our list, we're going to get the marked field. And if the current key is equal to the key and the marked field is true, is not true, then we're good. Okay, and here's so we had the window method with a find that we didn't tell you about. And you remember that we said that when we traverse the list, if we find something that's logically deleted, we're going to remove it. And so this is how that's going to work. So we're going to start from the head. We're going to start from the head, and we're going to get the predecessor and the current node. And then while true, we're going to get the successor node from the current node. And while that successor node is marked, that means it's deleted. We're going to do ... whatever that means. And otherwise, if the current key is greater than the key, is greater than or equal to the key, then we're going to return the window. Otherwise, we're going to update the predecessor and current nodes. So that's going to get the successor, and the details of that will be coming. That returns from the method, that advances. Okay, so here is the part that we snipped out, right? So we had on this one, we had that while marked, and we had ... So here's the while marked. We have the ... in the front and back instead, and we have while marked. And we're going to say the predecessor.next compare and set from current to successor false false. So this is an attempt to remove the marked node. And if this fails, we're going to retry. We're going to just start the whole operation over again. If it succeeds, we're going to set the current to the successor and the successor to the current.next.get marked. Okay, so this allows us to physically delete nodes as we traverse the list. Okay, so performance. And now we're going to show you some graphs of performance, which almost make sense. It was supposedly performed on a 16-node shared memory machine using our various Java list-based set algorithms. And they're going to vary the percentage of the method calls that are to contains. And so this is our throughput in here. So coarse grained and fine grained locking are the worst, and the lazy and the lock free ones are the best. And this is 90% contains. And then if you have 50% contains calls, then it's the picture is still a little different. We're still looking at lazy and lock free being the best. And then we go to some unspecified, oh, here is the percentage of the contains method, and here's our throughput with various different methods. So as the contains method gets higher and higher, the benefits of these things become stronger. So in summary, we have these 5 different methods that we've discussed. We've got coarse grained, fine grained, optimistic, lazy, and lock free. And there are 2 different views on, whether you should use locking or whether you should not use non-blocking algorithms. And there's different people who feel different ways. And the answer, it's sometimes nobler to compromise, combine locking and non-blocking. Lazy list combines blocking, add and remove, and weight-free contains. And sometimes that's the best thing to do. But blocking or non-blocking is a property of a method. Okay, so that is the lecture. What I need from you all now are questions. Alexander Tisdale, let's see, I haven't heard from you. Let's see, what can I ask of you? Because you haven't asked me anything, so I'm going to help you out. I'm going to ask you a question. Considering fine-grained locking and optimistic locking, which would you say is better and why?
I would think that optimistic locking would be better.
Why?
I'm trying to remember.
What's the reason why? Let's try it this way. What's the reason why it might not be better? What's the circumstance in which it wouldn't be better? Do you remember what we, go ahead.
No, what were you about to ask?
I was going to ask, do you remember we discussed pluses and minuses of the methods. So with fine grained, we did hand over hand locking. What did we do on optimistic?
Was that where we had 2 locks for each thread?
Well, no. I mean, well, yeah. Each thread had all of the fine grained, optimistic, and locking and lazy all had 2 locks. Each thread would get 2 locks. They would always lock the predecessor and the current. But what was the difference in the locking strategy with optimistic?
I can't remember.
Okay, let me ask you what I hope is an easier question. What was the key thing that we introduced with lazy synchronization? What was the new thing there?
There was the bit that logically removed it.
Right, a logical removal bit. Okay. Derek, would you like to ask a question, or would you like me to ask you a question?
I had a question about the lock-free synchronization. If you kind of go back to that for the beginning of that guy.
All right, so let's go back to the beginning of the lock-free.
So right here with the bit synchronization, right in here. Can you explain this part one more time about the cast and how the pointer and the work together about this?
Sure. So what we're going to do is first thing we do, right, is we're going to let me back up a little more to get to the front of. So we're going to use compare and set to verify the pointer is correct. This is before we introduce the combined pointer. So this one is going to say a logical removal. We're going to just mark that, and then we're going to compare and set this pointer to this object. Now, this is not going to be adequate, right? You see?
Yes.
Because what's going to happen is I'm going to have this one that's gonna go in here and it's gonna try to add. So we have a thread that's gonna come in here and mark that. Let's see. We have this green here. I would prefer this still showed green. And then on this one, we have red. And what's gonna happen is this thing, we wanted to add this thread, this node D here, and we looked at C and we saw a green. But then before we could do our compare and set, this other thread came in and marked it red. Okay, and so now what we've done when we've added is we put this, we think we've added a node, but we haven't, right? We have prevented a problem with two nodes trying to update this next field at the same time. But what we haven't fixed is the problem that these things happened at the same, this thing got changed on us. So what we're going to do is we're going to mark these, we're going to change these things together. Now what we're going to do is change this pointer from this next pointer to this D object, but at the same time, we're going to verify that the logical removal bit is not set. So we're going to still say that we're expecting this to be true, and we're going to update it to be true. But we're comparing and setting the mark bit and the next pointer at the same time.
Okay, I'm assuming that basically that's what that while loop, that while true is going to be checking the whole time, basically, correct? Is that what that's going to be doing? To check and make sure that it's not checking before we try it.
I have to go ahead to look at the code that you're talking about in order to.
Yeah, I think there's a while loop that you're checking.
Oh, there is. I just need to look at it. I can't just
I gotcha.
a while true loop, you know?
Yeah.
Hold on.
That's good.
So this loop, this outer loop.
Yes.
So that loop is that's a place that we're going to find ourselves at if we have contention. So if there's some other thread that's trying to work on this same data at the same time, right? That will cause some of us to fall through the logic below, and either that or we'll explicitly continue to the retry, or I'm sorry, that's not the retry. So what this removal is going to try to do, right? It's going to get its windows, it's going to check things, and if it's and if it doesn't find, if it finds the key, right? So it doesn't bail out here, then it's going to try to update the reference, and if it fails to update the reference, right? If it fails to do the compare and set from false to true on the bit, it's going to continue, and that's going to keep the loop going. But otherwise, it's going to do this compare and set, and it will be done.
Okay. Okay. Yeah. That makes more sense now. Okay. Thank you.
All right. Christopher Clark, would you like to ask me a question, or would you like to, would you like me to ask you a question, or would you like to ask me a question?
I guess I'll take a question.
You'll take a question. Okay, let's see. I have to think of one now. Well, let's ask you the same question I started with before. What is, if I'm looking at these various different things, what's the difference between optimistic and fine-grained locking?
With fine-grained locking, you have to walk down the linked list, doing that, locking successive nodes until you finally get to the ones you're looking for, right? Versus with optimistic locking, you just do a search until you find what it is that you're looking for and try and acquire the locks around that whenever you get there, as opposed to walking your way down.
And why might optimistic synchronization not do as well?
If you get into contention between threads that are both trying to acquire nodes near each other, and they're,
well, it's getting fewer locks. It's attempting to get fewer locks. Why might it still be slower? What is it doing? It's doing something additional that fine-grained doesn't do.
the validation that it can
The validation, and what does it do? How does it validate?
By having to do a search down the list
Right.
anyway without acquiring
Right.
blocks, just to make sure that you
Right.
can reach it from the head.
Right, it retraverses the list, and traversing the list twice could be expensive, especially if it's a long list. Okay. Christopher Vasquez, shall I ask you a question or will you ask me a question?
I'll ask a question. So, for all of these locks, I was wondering what would be like the ideal like application for like each type of these like locks and algorithms. Like when would you use each one?
So I think that the coarse grain locking you would use if you were just starting out, or you might even swap it in if you had a algorithm that you were, if you had if this was part of a bigger program and things weren't working and you suspected that you had made a mistake in your complicated lock-free synchronization, you might substitute in coarse grain locking during debugging just sort of to verify that, right? So if whatever problem you were seeing still happened with coarse grain locking, then you could figure that maybe your lock-free synchronization wasn't the problem.
Okay.
That would be a reason to do that one. The lazy synchronization, well, one of the things optimistic we already discussed, it's retraversing the list. I don't think that you would really ever use that. I just sort of see that as a logical step on the way to lazy. Lazy, on the other hand, is a very nice system, right? That marked bit really helps out a lot. And it's kind of just a nicer way to get around all the problems that we have with swinging the pointers and keeping track of what's still in the list. Lazy versus lock free, though, is the big question, and you may find that either one of those might perform better than the other in your experiments, and then you would just decide based on that.
Okay.
As I said, the problem is with hardware and optimizations is it's a very tricky game. I mean, the hardware is always a moving target. It's always doing different things, and what works well on one machine might not work well on another. So you always need to keep your options open and consider revisiting things. One of the key types of reasoning, though, that we want to teach you, want to make sure you come away with, is the difference between locking and weight free and those kinds of methods, because if you lose one of the participants in your parallel application, right, you want the thing to still make progress. A lot of times it depends on what you're doing, right? So there are some things where your reliability is the key, right? So you need to have a lock free because you can't afford to have things stop because a thread got lost. Now, on most SMPs, it's very unlikely that just one thread is going to be lost. But if you're using a bigger piece of hardware, if you've got threads on different nodes, then it becomes more likely. So anyway, hopefully that rambling answered your question.
Yeah, it did. Thanks.
All right. Does anybody else have any other thoughts, questions, comments, updates on your personal life? Commentary. No, let's not do that. All right. Well, if there is nothing else, then I thank you for joining in, and we'll see you all either Thursday, Friday, or next week.